All right. Hello, everyone. Can people on Zoom hear me and see my slides?
Yes.
Yes? Okay, perfect. All right. So let me see. I hope people can hear me. It's like a pretty funny setup. But okay. Yeah, so thanks for the invitation and thank you very much for the introduction. So today I'm gonna mainly talk about work that was done by these students that you see here, on the bottom of the slide. And I'm gonna talk about specifically contact-rich manipulation and focus on that. But before I do that, I want to talk a little bit about work by Tyler and Kusha, who are sitting right here. But they will go way more in detail with you and have posters, and I will just give you a really quick overview of this. But starting with this, I just wanted to get your attention to, let me actually get rid of these things. Get your attention to the fact that it's actually pretty amazing what two-fingered grippers can do compared to dexterous hands. And here are just two videos that are playing now. So this is from Generalist. I'm sure many of you have seen this one. And maybe this one is less well known. This is a recording from an ICRA workshop talk by Maria Balza at the Dexterous Hands workshop actually there. And she showed this video that I had seen before and found really impressive, but they don't have it kind of publicly available. And so what you see here is their setup with the two Franca arms solving one of the NIST board tasks, one with the gears. And you see like on the left side, there's actually a person trying to do the same task that the robots do on the right side. So she's trying to put like a belt around these two gears. And she's actually struggling a lot because the belts are actually quite stiff and not very flexible. But the robots with the two grippers actually manage quite well. And so I think many people are even asking like, oh, do we actually need more than two fingers? And so for me, I wanted to motivate a little bit about why dexterous hands and working on dexterous hands with multiple fingers is actually very interesting. First of all, it's of course a hard problem, which makes it interesting for me as a researcher. But the real reason is that I think the dexterous hand will ultimately provide better throughput, right? Like that is visualized here with this little drawing of this pipe and the water flowing through it. And so I think they get greater throughput just by an increased amount of dexterity. And they also provide quite an amount of controllability by actually providing more controllable subspaces in the manipulation problem. And so I want to explain a little bit of what I mean by this. So first of all, I want to make the case for why dexterous hand provide higher throughput. So this is a video that Tyler actually found online. And let me just play it. It goes really fast. So this is a person who is, I don't know, screwing a screw into this piece of wood using some tool. And again, it goes really fast. So let's see what's actually happening. So let's slow this one down. And so first of all, you see this by manual coordination, and then you see this person picking up the tool and really doing some really quick rearrangement in the hand, rotating it around different axes, and then again, like coordinating these two hands, doing failure recovery, all things you actually don't really see in the fast video, but it becomes much more apparent in the slowed out version of it. And so none of these things that the person has especially done with their right hand, you could really do with a gripper, right? Like, or at least you would need to do it maybe through handover or using the environment, would probably take much longer. So that's one example that shows like why dexterous hand actually increase throughput. And then here is an example that should exemplify what I mean by a dexterous hand providing more controllable subspaces. And this comes actually from a work from Aude Billard from EPFL, and she shared actually with me these videos that she had. And what they did in this work, and you see the references down there, is they studied Swiss watchmakers and how they learned to become so good at what they're doing. And they actually, have to, of course, manipulate the tiniest parts with the tiniest tools and all of this. And so they studied apprentices for many years and how they solved actually tasks. And you see kind of their hands are instrumented. And here you see a beginner actually doing this task of using this tool, aligning it, and then screwing this tiny screw. And you see like this beginner is basically using both hands for quite a while to actually do this alignment between this little screwdriver and the screw. And then you see what happens with an expert. So this expert, first of all, aligns much faster. And then the second hand, the left hand in this case, is not used anymore, actually at all. What they do use is their pinky finger to actually stabilize this, this little tool. And so in this paper by Otbiya, they actually try to reproduce that by analyzing actually the subspaces. And they show that by using this pinky finger, actually they make the amount, they've basically reduced the amount of controllable or free degrees of freedom to actually do this task. So really interesting. And by the way, over these 2 years that these people learn this, this strategy emerges by basically the majority of the apprentices as well. And it's also quite interesting about what kind of instructions they actually get. Very little, by the way. They just keep practicing it. Okay, so that's where I think dexterous hands, or why dexterous hands are actually really interesting to study, because if we really truly want to bring value to people at some point with our robotics solutions, then we should think about how we make these robots actually perform really well at these tasks, maybe even better than humans. Okay, but of course, dexterous manipulation is really hard. So this is a video from Sim Tool Reel. And it just shows that, that here we have to control these 22 degrees of freedom of the hand, but then also 7 degrees of freedom of the arm. There's like multiple context switches that come from these different tasks, like grasping of the table and rotating the tool and using the tool as well. And finally, all of this runs, you notice this is a 1x speed of this video, and you see, and also this control has to happen at 60 hertz. So this is really quite a hard problem. And we made some really cool progress on this in this work called Sim to Real. And it will be presented here at this conference on July 15th in the RL session at 5 to 5:40 p.m. And afterwards, there's a poster session. So you should come and ask Tyler and Kushal here for all the details. And yeah, and the cool thing about, I'm not going to go in detail because there's going to be a spotlight later by these two. But basically, the cool thing about this is that essentially, let me see where my mouse is. I want to click this thing away. Can't see it. Anyway, so you basically what is happening here is that all of these different tasks that are done with a single policy and with objects that the robot has never seen during training, and also on doing tasks that actually the robot has never seen during training as well. Again, this is just a little teaser. If you haven't seen this work on Tyler and Kushal, you can drill them with questions as well later. And so this particular policy actually is really good at doing these kind of goal-reaching tasks of the objects. But we also found that it's not super good at assembly, especially when the clearance is basically very tight. So when you have to be very precise. And so as a follow-up work to Sim to Real, we have this work called Play to Perfect, where we actually looked at using this kind of pre-training, post-training recipe in VLAs and so on, if we can also apply this to RL. And so we studied how the Sim to Real play policy, as we call it, can be a good starting point for dexterous assembly task. And so basically what we found is that we can basically really quickly fine-tune a play policy to do these more dexterous assembly tasks that require precision. And I think what's really cool about these videos for me personally is to see this kind of failure recovery behavior and this very natural behavior of the hand. Although we actually never used any human videos or something like this, this is a purely object-centric policy as well. And again, Tyler and Kushal are going to talk much more about this today. And they will have a poster exactly on this work here at this workshop. Okay, so, but today, because Tyler and Kushal are here, I'm going to focus on a little bit something different that also has to do something with dexterity. So I want to play these two videos again. And now I want you to not pay attention to the fact that these are grippers, but more to the fact that these are actually very contact-rich tasks that are done here, okay? And so I think there's an ongoing debate between people in this kind of VLA imitation learning space who usually only use images, and people who believe in tactile sensing on whether actually tactile sensing is needed at all. And so if you look at these videos, it's definitely personally really surprising to me how effective VLAs and diffusion policies actually are in contact-rich tasks at all, right? Like, so again, none of these works use any contact sensing whatsoever. And I think people are still insisting you need, and eventually you will need tactile sensing, and the people on this side of the aisle are like, no, look, we can do all these things without. And so I really wondered, why are these things so effective at these tasks? And I think what's happening is that these imitation learned policies, they learn forceful interactions implicitly to some extent. So here is just like a schematic drawing of a Franke arm pushing against some box. And usually when you teleoperate this task for just pushing against this, you would use some device like this Oculus controller or maybe a Jello, whatever you use, and then actually command an action that is inside of this object, right? And so, of course, because this is a rigid object, this box, the robot would make contact at this blue dot, and then the distance between the actual contact point, so the observed end effector position, and the commanded action is proportional to the applied force. So if you wanted to, and so usually these IL policies, they are not trained on the observed end effector position, of course, but on the commanded actions. And so if you wanted to apply more force, for some reason, you just basically command the action further into this rigid object. And so because the distance increases between the end effector position and the commanded action, the applied force will also be bigger. So basically impedance control, right? So on the left, you push with less force. On the right, you push with more force. And and I think because imitation learned policies are trained on these commanded action, they learn to relate the language instruction and the visual input to the desired applied force, and therefore the policy outputs an appropriate commanded action, which is proportional to the applied force as well. And so I have a case study for this that we did actually last year in DexForce, and there we kind of used this principle. We used it with kinesthetic demonstration, and the details of this, I don't want to explain so much why we did kinesthetic demonstrations for Dexterous hand, but basically what we basically exploited here is the same principle. So we actually have force-shock sensors at the end effector or at the fingertips of this Allegro hand in this case. These are coin-sized force-shock sensors developed by Mike Rutkowski's lab. They're called CoinFT. And so by using these, we can measure the contact force and also from proprioception get the observed fingertip position during these demonstrations. And then we can use this to label the actions that is actually supposed to be learned through behavior cloning. So if we want to push with less force, then the commanded action will basically be at this place. If we want to push with more force, the commanded actions will be further in. And again, we measure this with this force-shock sensor at the fingertips. And so now, if we use these commanded actions to actually learn a diffusion policy, and this diffusion policy in this case can actually do this fairly intricate task where forces have to be balanced quite deliberately. So here is kind of I think it's actually a replay of the demonstration doing this task. And the controller is basically commanded to this orange position rather than to the observed fingertip position. And if you do the opposite, you actually have a replay where the controller just goes to the observed fingertip position. You can imagine what happens. Basically, this little battery is essentially going to slip out of the fingers, and it's not going to work. Okay, so this is a complete failure. So the point is that if you do imitation learning, you should actually learn from these force-informed targets. And so if you don't do that, you basically get 0% success. Sorry. So here are the kinds of tasks that we did in this particular work that we evaluated, and we get like 76% success rate. And if we don't do this training on the force-informed action, we basically get 0 success rate. Okay, so we use basically tactile sensor information to label the actions for imitation learning with the commanded actions. But what many people do as well is to actually use these tactile sensor data, or in our case, this force talk information from the fingertips, as observations next to the visual input as well. And we wanted to know, like, okay, if we do that as well, we additional feed in the force observations into the DexForce policies. In addition to vision, do we get anything out of this? And so if we don't use these force observations as sensory input to a policy, we can still do quite well. It definitely, if we add it, it never hurts performance. But it only really helps in a statistically significant sense for some of these actions. For others, it's not statistically significant, the actual increase of including these force information as a sensor observation. Okay, so this is just to, you can walk away now with a few take-home messages. First of all, these VLA policies, they probably work because implicitly they have to somehow learn how to apply, how much force to actually apply. That's really where we found, in DexForce at least, that's the secret source of not needing actually an explicit force talk sensor or any other tactile sensor. And if you do include force observation, it helps only for some tasks, okay? Okay, so what does it mean for VLAs, for example? So there's, of course, some work that tries, because the belief is that you have to include tactile sensing to become even better at manipulation tasks. People study how to inject force information into these massive VLA models. Here's 2 works that have done this, 2 related works. Again, like DexForce looked at single task diffusion policies. These are VLAs, which are multitasks. Of course, this tactile data only comes in during post-training and not during pre-training. And so usually these related works, they frame contact-rich manipulation as a force sensing problem, and they leave somehow unexamined where failures actually come from, either during training or if they really come from a missing sensor modality. And usually they only append vision alongside, they usually append tactile information alongside vision and proprioception. And as we've seen in DexForce, that doesn't really help all the time, right? So what we wanted to really look at why, or we wanted to really understand like what tasks are actually helped by tactile sensing. So this work that I'm going to talk about is not yet out on arXiv, so I'm sorry for this. It will come out soon, but I want to give you some results anyway from this. And I'm kind of losing track, like how much more time I have, because we started a little bit differently. It's like 5:30. Okay. Okay. So till 35. Okay. So first of all, what we found is that there are actually 2 distinct failure modes in contact-rich contact-rich tasks that are typically conflated in related work. And so let's first look at a success by in a contact-rich task. So this is inserting a plug into a socket. And so you see this kind of animation that shows this. And on the right side here, you see the kind of correct force profile of everything goes correct, right? Like, so there's 0 force, and suddenly contact force ramps up. And maybe the robot or you are searching for the right alignment. So the force plateau is kind of flat, and then it drops when you actually insert. And once the seating force is reached, so you really insert it all the way, the contact force spikes again and the task is successful. Okay, so then again, we found that there are actually 2 kinds of different failure modes that require different strategies on how to address them. The first is a precision failure. So maybe in this case, the alignment between this plug and the socket actually doesn't work quite well. So you see the force profile actually looks quite different at the end, right? Like, so it basically makes contact, ramps up contact, but then never really finds the alignment, so the contact stays flat. Or we have force failures where you actually get the alignment right, but don't insert all the way. So the seating force never is felt in this force profile. So these are the two types of very different failures that have different causes in contact-rich tasks. And so we looked much more deeply at this to try to find what is actually going on. So here is what we identified as the cause of precision failures. And it's basically that when you have a precision task, during reaching, these VLA policies, they basically output delta position of the end effector. And while you're reaching, these deltas, these changes in end effector pose are actually quite large, right? Like, so this is what you see at the beginning. Then you make contact. And then when the robot is actually needs to kind of find this alignment, these end effector adjustments are actually kind of small. They are almost zero. They almost collapse to zero. And the problem is that this is actually not really learned very well with the current way these VLAs actually set up. So what is happening is that in VLAs, you typically have a denoising schedule that looks like something like this beta schedule. So they go, VLAs, they go from on the top, these kind of noisy, very noisy action chunks, and then they denoise them gradually using this denoising schedule, which is typically this beta schedule that comes from vision. Here you see like animation of this, right? Like, so you gradually denoise this action chunk at inference, but really at the contact correction regime where you need like minuscule little adjustments, there's almost no gradient signal that is actually coming from this particular contact correction regime. So the policy will never learn to really make these really small adjustments. And so the way we address this is to actually come up with a very different denoising scheme, logit normal denoising schedule, basically, that concentrates much more gradient signal in this contact correction regime than this original beta schedule as well. And so if we apply this at at post-training and also at inference, we don't need any extra parameters. We don't need any extra data than you anyway need for post-training, for example, or we don't need to make any architectural changes. So this is really like a plug-in thing that you can do with any kind of VLA backbone that uses a flow matching head. And so here you see kind of a side-by-side comparison of using pi 0.5 in this example and pi 0.5 plus this new denoising schedule that we call LN here. Let me just play this kind of at the same time. And so you see like pi 0.5 actually gets stuck. Again, it can't do these like small adjustments. And if you include it with this, kind of like plug-in new denoising schedule, you actually get much better precision. And again, this is without any force sensing, by the way, as well, right? Because we are only addressing these precision failures, not force failures. Okay, so now let's go to the second cause of failure in contact-rich task, or what typically people think of contact-rich task, and that comes from the force from the structure of the force signal itself. So there are three properties that a force signal has that current architectures or related work actually fail to exploit. One is that in free space, the contact is actually nearly zero, and really not. It's really only becomes informative when there is contact happening. And then also the force signal actually carries temporal structure. What matters is not only the current value, but actually how you got to that value as well. So the instantaneous measurement encodes the current interaction state, but recent history also kind of encodes the dynamics that led to it, including transients and cumulative force buildup and things like that. And then the other thing is that really the influence of the force on the policy should depend on the contact state. And in free space, basically, force readings should be effectively ignored, and contact, even small deviation, should trigger corrective actions. And so we basically made modifications to these VLA policies to address these force failures. And so what we did is basically we first of all add a time-aware force injection. So basically, the current force reading enters at every norm layer and modulates the policy's sensitivity to contact. And then we also add a short force history as a token to the decoder. And it basically allows the policy to reason about contact dynamics. And we also actually use some kind of contact gating that forces the encoder to only update at contact as well. So these are the three additions that we make to this architecture that address basically these two very distinct failures. And we evaluated on whether this matters. And I know I'm out of time, so I'm going to skip a little bit over these tasks that we selected. But we were very deliberate about making sure we have both precision critical and force critical tasks. And we basically found that there is basically different tasks leverage or benefit differently from these two different measures. So if you look at this, you basically see that force critical tasks benefit the most from this force injection, while the precision tasks actually don't care about actually any force sensing or tactile sensing at all. And by the way, wiping, which is a very popular task in these kinds of papers, is actually super well solved by just having a decent compliant controller, and you're fine with that. One more thing is that if we looked more closely at the related work as well, and we wanted to know, do they actually pay attention to force measurement, because they have a very different architecture. And so instead of using the actual force signal, we actually injected either zero or just IID noise instead. And basically, the message is that while our method performance actually drops significantly, the baselines don't really drop at all. And they don't really pay attention to the force signal. And we think it's probably because that force is useful, not because it's a force signal, but it actually acts as a regularizer during training. Okay, so this was my talk. And this is basically the last slide, where I dove a little bit deeper into why VLAs are actually so good at force and precision tasks, and why they maybe fail at certain tasks, and certain tasks are fine. So thank you very much for your attention. I'm happy to take questions, and as many questions as is possible given the remaining time. Thank you.
While you're doing that.
Yep.
All right. Weiming Z is a tenure track assistant professor lecturer at the School of Computer Science at the University of Sydney. His research focuses on enabling robots to perceive, reason, and act effectively in complex environments. Combines ideas from perception, motion generation, probabilistic modeling, and control. Before University of Sydney, he was a postdoc at Carnegie Mellon, which actually we met.
Yeah.
And before that, he was a PhD student with Fabio Ramos at University of Sydney. His work has received several distinctions, including the 2022 Learning for Dynamics and Control Best Paper Award, selection as an RSS Pioneer in 2020, and the University of Sydney School of Computer Science Outstanding Thesis Award. Thank you for being here.
Thanks for the kind introduction, Kenny.
Are you screen sharing?
The screen share keeps dying.
Oh, because you're on your browser. Do you have Zoom? Do you have Zoom downloaded?
I'm one of these people who kind of just use the browser.
Okay, well then, do you want to send me your slides?
I'm gonna try again. Does it drop?
This is the normal problem with browsers. Can't do full screen.
Okay. How about I just should I?
Or do you want to just do it in wait, let's try something. Let's try
Okay.
screen go into PowerPoint, then try to screen
Yep.
share.
Okay, I'm in PowerPoint now.
Okay, so make it
Okay.
make it full. Now try to hit screen share on the top. Does the Zoom button thing even come up? Oh, I guess it won't because you're not on the app.
Oh no.
Uh,
Okay, now let me go back to my browser
Can you
and
start
then
it now?
and then let's start.
Can you just do the whole screen? If you do
Yep.
an individual thing, it may not.
Yes.
That
Okay.
works. That works. That works.
Oh, okay, that works.
You're good.
It's magic. Thanks for the kind introduction, Kenny. And thanks for the invite.
Maybe you should. Yeah.
Cool. Yep. So I'm just going to speak in this direction. Hopefully that works out. So today I'm going to be talking about imitation learning on high-dimensional robot systems. So some of this is going to be on dexterous manipulation, but it's also going to be on mobile manipulators and also teams of mobile manipulators. So stay tuned.
Unable to move forward now.
Yes. Oh, no. Okay. It seems to work. Cool. So a lot of the cool demos and like advances that we see these days are somewhat of the result that data is easier to collect and we can train visual motor policies on them. And a lot of this has arisen due to better teleopt devices. So this includes kind of leader-follower setups, but also setups that like Yumis and other things. But for leader-follower setups, this paradigm is oftentimes tricky to directly translate to higher dimensional systems, including, for example, mobile manipulators, or going from parallel jaw grippers to multi-finger hands with a lot of degrees of freedom, and also to collect demonstrations for kind of more than one robot at once coordinating. And a lot of this has to do with kind of the mental load that the operator has to kind of endure while they're doing this teleoperation. Oops. Let me actually mute or tune my. Okay. So it seems like the videos are fairly loud, but okay. And the first work that I'm going to be talking about is something that we've recently archived. I'm going to be talking about the mobile manipulation part of this like high dimensional system theme before the dexterous manipulation. But the first work is around an open source whole body bimanual mobile teleop system that we've recently released. So this is a fairly low cost. The whole thing can be set up under $100 US. It's the main cost is the two servos in a system. So it consists of kind of leader follower setups and also a foot pedal. So this is in contrast to kind of mobile aloha type settings where the operator needs to like physically push something like a cart and then do the teleopt. In this setup, we're able to actually remotely teleop over a distance. And in particular, the kind of main contributions around this are kind of a set of cues that actually guide the teleoperator. So some of our design choices, we have force feedback on the arms, and we actually use these signals later on to train our policies. We have essentially a nudge on the foot pedal when the mobile manipulator is getting close to various obstacles, and these cues then enable the operator to kind of be aware of the obstacle. And also something we call manipulability guidance. This is essentially when the arms are overextended. The foot pedal helps kind of nudge in directions of higher manipulability, so that the arm can kind of reach. And we'll see some examples of how this is helpful in a bit. So force feedback on the arms, we found this to be kind of this haptic feedback back to the operator to be hugely important. This enables the tele operator, when they're in another room looking through the camera views, to do things like maintain contact with surfaces. So here's an example where the teleoperator can roll a roller over a surface. And also in settings where we need to kind of rigidly hold onto something and swing it around. So for example, this rod, if you don't have this feedback, it's hard to maintain this like rigid transformation. So here's an example where we can like quickly kind of rotate this rod and then move through narrow passages. Cool. So another design choice was around this proximity-based pedal resistance. Essentially, what we've found is that kind of perception obstruction is kind of an issue when you're at a distance from the mobile manipulator. So in the mobile Aloha setup, if the human is right behind the manipulator, you can kind of adjust your neck and kind of look around. But oftentimes in many of these settings, as the bimanual manipulator is holding on to something, you have the issue of like cameras being obstructed, and as the mobile manipulator is heading towards obstacles, having like a force feedback on the pedal, it enables the operator to smoothly navigate. So here is an example where, as you see here, the top camera has been obstructed by this like live box, but regardless of this, the operator is able to like kind of swerve through the environment and do this mobile pick and place task. Cool. And now the last kind of bit of design choice, or a novel design choice here, is this manipulability guidance, where the pedal actually kind of co-pilots the operator to nudge the mobile base towards a certain direction. So manipulability measures how easily the arm can move at a certain position. So if it's kind of overextended at the edges of the workspace of the arm, what happens here is you would actually want the operator to kind of move closer to a direction that enables the robot, the manipulator, to reach whatever it's trying to reach. And so, with this nudging, we get this behavior of, here's an example where the robot picked up a glove from one side of the shelf, needs to transfer over, place it on the other side, and then it becomes overextended. And what we need there is for the base to kind of, or the user to kind of slowly nudge the base towards the other side. And with this guidance, we're actually able to do that. You know, as with all papers, you know, we demonstrate some numbers here. Essentially, we have higher teleop success rates and lower completion times in constrained environments. That's pretty obvious because in these constrained environments, you have the guidance on the foot pedal, and also under limited perception as you're close to obstacles. And we enable for greater reachability and smoother contact because of the guidance around the manipulability. And we also do a user study showing that that the kind of operator task load or the mental load on the operator significantly benefits from having these feedback cues. So here is an example of this like uncut, essentially 10-minute run of teleopt in a kitchen. And so this is like very long duration, and we can do it kind of uncut in one go. So we demonstrate various kind of contact-rich behaviors, including opening fridge doors, unscrewing various caps, opening the door of the microwave. So here we can unscrew caps. So there's force feedback on the kind of clutch of the leader arm based on kind of the resistance at the gripper. And we also see someone there that was wiping a table as well. The point is, we're able to do very long horizon teleopt and collect very long duration data. And we're able to train with high quality data. We're actually able to train. Fairly long duration policies, not as long duration, of course, as what we can teleopt, but interestingly, including the joint talks that we actually use again for the force feedback. If we include it in the policy, we see improvements. Also, co-training with a bit of upper body data helps a lot. Cool. Now we'll be switching gears to thinking about kind of extend teleops to or leader follower setups to Dex hands. So in the literature, people have oftentimes looked at settings where instead of like a leader clutch, there's some sort of like camera that's like capturing the hand pose, and kind of through media pipe or something, you then get the hand pose and then do some sort of retargeting onto the Dex hand. And when we first got our Dex hands in the lab, we tried to do something similar, but then we realized that the kind of mental load was really heavy, and also it was oftentimes difficult to handle the manipulator while you're doing hand gestures on the hand. So we were thinking about whether it's possible to essentially map kind of clutch inputs to various kind of Dex hand actions. And it turned out that we were able to do that, and we did that through decoupling lightweight policies for the hand during teleopt. And the key idea here is not to kind of use RGB systems to like teleopt the fingers at every frame, but instead something that we found to be very effective is to this is almost like co-training. It's like collecting hand-only demonstrations using vision to do retargeting, we then train a set of like lightweight hand-only policies. And then while the human is teleopting the arms, there's a VLM in the background that continuously switches the correct kind of hand policy. And then this hand policy is controlled by the clutch. And what the clutch does is essentially trigger a policy rollout for the Dex hand and also enable rewinding back. Okay. And here is an example of kind of a fairly long duration teleop that we were able to achieve with this. As you can see, multiple lightweight policies can be switched around seamlessly. And so we can do things like tool use and also use the Dex hand to press a button, but then switch to another kind of hand policy in the background with the VLM and do grasping. Cool. And this enables us to, of course, efficiently collect demonstrations to train visual motor policies. So here are some examples of the various policies that we're able to quite efficiently collect data and train for. And so we see again that that we can like seamlessly. So even though this is kind of decoupled, we can seamlessly switch the various mini hand policies. So here we have an example of picking multiple objects. Cool. And the last bit, I'm going to be talking about something that's kind of even more high dimensional, which is trying to think about systems to provide demonstrations to coordinated to multiple robots. So as I'm short on time, I'm going to just quickly go through what we can achieve. Here's an example of like coordinated 3-arm. So this is an autonomous policy, 3 arms operating, and we see kind of coordinated behavior. And a recent work that we archived has been around kind of systems to kind of coordinate multiple mobile manipulators. Here's an example of kind of coordinated behavior where multiple mobile manipulators kind of work together to carry things around and to do tasks. Do I still have a minute? No. Okay. So we also see tasks here that require very good timing, where we have 2 mobile manipulators, and this is also fairly tricky because this requires rigid, like a rigid transformation across the grippers. So. Cool. So quick takeaways. So a good teleopt interfaces improves performance, especially in settings where we actually are confined to a lab, so we don't have like 10,000 hours of data. Local autonomy reduces operator burden, so having these like small lightweight policies really helps. And also we can essentially enable multi-robot imitation learning from a staging process. Happy to talk more about this if you find me offline. Thanks a lot.
Thank you for the talk. I think we're running short on time, so we're going to move to the spotlights now. If you have questions, maybe you can see him during the break after spotlights, or.
Okay, so I represent the Ego engine. This is a framework that's turned the egocentric human videos into the high fidelity that shows robot demonstration. So the idea is very simple. Instead of relying on the expensive robot teleoperation, we use the egocentric human video as a scalable source of robot experience. Even with human control, teleoperation is very hard and also expensive. The Dexterous manipulation remains slow, fragile, and hard to scale. So that's why we introduced Ego Engine. It is a scalable data engine that converts egocentric human video into the robot demonstration for zero-shot policy learning. Given a very simple egocentric human video, we first reconstruct the scenes as a digital twin. Then we have a visual branch that removes the human hand with video in painting and rendering. And then we have an action branch that retarget the human motion and also have an object-centric refinement to an executable trajectory. With this two-branch framework, Ego Engine is able to produce a high-fidelity synthetic robot observation video. Here is a demonstration of how human converted to the robot video. And it can temporarily align the robot video. And also our method is able to provide a video that are more similar to the real teleoperated robot demonstration from the visual side. The action branch is able to refine the trajectory. This is able to refine the retarget trajectory that failed to execute the task in simulation into the executable ones in the real world. So our method has the best performance efficiency trade-off. The generated data is able to support zero-shot policy training. We test on 4 tasks. Either is simulation, it is the replay in the simulation, and also execute in the real world. Also, it is a rendering video. So across the 4 real robot tasks, Ego Engine enables zero-shot policy execution from the generated demonstrations. It even achieved a performance that is comparable to the teleoperation data. Ego Engine is a scalable data, sorry.
Yeah, to finish up there.
Okay, it is scalable engine across many digital twins with the view-to-scene technique. Also, the policy performs improve with the data scale up, the same as the teleoperation. At a larger scale, it has the potential to convert a massive egocentric video dataset into the robot demonstration. Our method has very fast speed for data generation, so the action generation is the main bottleneck of speed. Ego Engine uses the MTCS mode switching to adaptively select replay NPCs or reinforcement learning. This improves the efficiencies while preserving the executable trajectory generation. So comparing with the teleoperation data, it has more benefit for the fine-grained Dexterous manipulation task.
You need to keep moving.
Okay, it's allows. Okay, so by turning egocentric human video into the executable robot demonstration, Ego Engines reduce the expensive teleoperated data and enable zero-shot Dexterous policy learning. That's it. Thank you.
Sorry, where do I go?
Here.
All right, next we'll have touch improves learning, dexterous grasping from demonstration. If you have issues with your slides, come to me in the back. I will download them to my laptop, a fresh version, even if they were due yesterday. Okay.
Hello, I'm Pankuri, and I'll be presenting this work, which is done in collaboration with Nicholas from TU Dresden. So we have seen vision-only policies, and we are aware of limitations in that. they struggle with environmental changes such as dynamic lighting, shadows, or they also struggle if you are trying to generalize them to novel objects. And even if they know what to do or where to do, the contact awareness is limited. And this becomes more prominent when we are moving beyond binary grippers to dexterous hands, where there is more occlusion and their tactile can provide natural interaction and more contact awareness and dexterous control. So we have works in imitation learning side and individual works in tactile side, but we decided to explore and do a systematic study to identify like which tactile representations and which policy architectures and backbones can lead to good performance, or how does it work when you go into grasping tasks specifically for dexterous manipulation. So in this work, we have a system setup where we use a Franka robot, which has a Tilburg hand, and it's a four-fingered hand with digit 360 sensors. We collect demonstrations using Meta Quest 3 via Teleoperation pipeline. And we try to research into four primary research questions with grasping tasks. So let's go into the results of our study one by one. So we collected demonstrations on multiple objects, but during training, we only trained on 2 objects. And in our study, we showed that when we introduce tactile sensing, be it in XLSTM, Mamba, or transformer-based backbone, with simple CNN-based tactile representation, or a pre-trained encoder representation like SPERSH-X, tactile sensing in general tends to improve success rates in all of the policies. Oh, video is not playing, but yeah. And to stress test our work further, we extended this evaluation to large 20 objects. And there we see that with SPERSH-X tactile, the performance outperforms vision only by a huge margin. And this gain is more noticeable in larger and heavier objects. Secondly, with environmental robustness, we see in dim lighting, purple lighting, or even when the lighting is off, SPERSH-X-based policies, they tend to retain higher performance. And even in
Finish up. Yeah, we're running really behind.
Yeah, in low lighting, we see even when it's able to grasp, initially it tends to drop the object quickly, whereas the performance retention is much higher in darker ones. And our takeaway is, in general, touch helps in dexterous manipulation in grasping. Thank you.
Well, thank you. What's the next one? Next we will have, I think, it's a cross-embodiment robot manipulation. Yeah, via a unified hand action space. We'll have to be kind of strict on timing just because we're falling behind. Sorry.
Okay, I'm going to present our work, cross-embodiment robot manipulation, via unified hand action space. This is a joint work with Dr. Wang Xinjing's group from Arizona State University. So the problem we're trying to address in this work is, can we find a unified action space for different robot hands? With such a unified action space, we can leverage data from all different robots, including humans, to train robot foundation models. So our idea in this work is, let's use a sphere to align robot hands. Basically, because any gripper, any hand can grasp a sphere, otherwise the hand won't be that useful. And you will see spheres have some beautiful properties for control. So starting from a hand grasping a sphere, we first sample some points on the sphere. We compute the surface normal of these points, and each point is associated with spherical coordinates, lambda and phi. So we can transfer these spherical coordinates to the hands. That's our representation. So we call this representation the unified hand action space. And next, let's see how can we use this sphere to control any robot hands. Our idea is the deformation of the sphere will drive how this hand should move, because the hands need to touch the sphere correctly. And our action space, which is here, is the deformation of the sphere. So deforming every point on the sphere is too expensive. What we do is we define some driving planes, which can move left and right, and we define some driving vectors on the plan. So this point move inside outside. Given a deformed sphere, we can solve a cascaded inverse kinematics where we solve the hand joint one by one, such that the hand will touch the sphere correctly. So for experiments, we did an in-hand manipulation where the task is to locate a cube to a target orientation. We train our RL policy with the PPO in ISAC lab and using our sphere controller. So in this case, the action space is the driving planes and the driving vectors, which is shared by any hands. So first of all, we train a policy for each hand, and we verify that all these 4 hands can solve this task. We can also train a policy with 4 hands jointly, because the action is shared by all these hands. The task can be solved by all the hands. But more importantly, we show that we train on 3 hands, and 0 shot test on new hands, it can solve the task, because basically the action space is shared, and we solve IK using the after the sphere controller. So for real-world experiments, we did a lip hand and allegor hand. Then we basically do a sim to real transfer. So you can see these results from the lip hand and some results of the allegor hand. So feel free to talk to me at the poster. Thank you.
Thank you. All right, next I think we'll have DexX, is that right?
Hello, everyone. I'm Kai Feng. Let me introduce our work, DexX, learning visual tactile Dexterous manipulation from human videos. Human videos show you how a hand moves, but not how it feels. So our solution is decouple motion and interaction. We argue that simulation can serve as a tactile compilation engine. And the method can be concluded as 2 stages. In the first stage, we reconstruct hand-object interaction from monocular videos. And we train a privileged expert policy with PPO. The input for the actor includes hand-object target, proprio, 3D force, and object pose. And also the input for the critic includes future targets and privileged observations. In the second stage, we distill this policy into a point cloud-based visual policy with a dagger training pipeline. DexX outperforms baselines on multitask manipulation. It achieves 65.9% success rate across 8 categories of multi-stage manipulation tasks. Ablation study shows that 3D force augmented point clouds have better performance across tasks as a scene representation. And we also transfer this policy 0 shot to real-world hardwares. And we show that context-rich manipulation stage is the bottleneck for real-world transfer. And the sim-to-real contact behavior is consistent, not just the motion. Thank you.
Great, thank you.
Good. Which one's next?
Thank you. Perfect.
Okay.
All right, next we'll have Play to Perfect, is that right?
Let me stop share 1 second.
Yeah.
And
Maybe
make sure that, yeah. Then 1 second, let me just share on Zoom again.
Yeah. Okay. You good?
Yep.
Did you start?
Yeah, go for it.
All right. Hi, everyone. My name's Tyler,
And I'm Kushal.
and we're presenting Play to Perfect. Our goal is to learn precise contact-rich assembly with dexterous hands, but learning these skills from scratch is very difficult. Before we can learn the hard problem of precise assembly, we first learn the easier problem of playing with objects. We propose Play to Perfect, a framework for learning a shared dexterous prior via task-agnostic play, fine-tuning that prior for downstream assembly, and then deploying the policy zero-shot in the real world. Learning from play enables very fast training on downstream assembly tasks, and the resulting policies learn robust strategies. Play to Perfect learns stable multi-finger grasps that can resist force perturbations, while from scratch policies learn brittle thumb-only strategies that fail under perturbation. But the type of play matters. For play to be useful for downstream assembly, it requires diverse objects, a training objective that rewards both controlling the object position and orientation, trajectory diversity, and goal precision. Play to Perfect can learn diverse assembly tasks, including screwing, multi-part assembly, and tight insertion.
We evaluate the policy on different hole clearances, going from down to 0.5 mm. At 10 mm, the policy has a relatively easier job. But at tighter clearances, it's not just being precise, it's reasoning about contact, finding the hole alignment after missing it initially, and then completing the task. And we evaluated through different initial states. What's interesting to see here is the different strategies for grasping, reorienting, and completing the task. In some cases, it also fails, which is interesting to see and how it recovers. Here's the two failures highlighted here. What the policy does is it initially makes a misgrasp or a misalignment, but it can quickly go back again and recover. This kind of recovery behavior is learned through reinforcement learning in simulation, where the policy learns from its own trial and error behavior, and it fails in simulation, learns from that, and recovers from it. To make this more clear, here's a video at 0.5x where we pause the key interactions. Here you can really see the micro corrections and recoveries that the policy makes throughout the task. Here's a QR code highlighting our website, and look forward to seeing you guys at the poster.
Great, thank you. Next, we will have Craft, a tendon-driven hand with hybrid hard soft compliance. Sorry.
No, you're good. We present Craft, a tendon-driven hand with hybrid hard soft compliance. Inserting and twisting a key requires compliance because the key and the keyhole are never perfectly aligned. Compliance means that a finger is rigid enough to maintain structure, but soft enough to deform when needed. During key insertion, compliance lets the key ship so it doesn't jam, and during rotation, compliance reduces the twisting force on the key when the lock resists turning.
Towards this end, we introduced Craft Hand, a tendon-driven anthropomorphic hand. So our hybrid finger structure uses a rigid PLA on the outside for structural alignment and soft TPU joints on the inside for elastic deformation, and the metal dowel pins holds the structure. So combining hard and soft materials, we have the first joint, the dip joint, and the second joint, the pip joint. So Craft uses a rolling contact joint where the two curved surfaces roll against each other rather than rotating around a fixed axis, which it differentiates it from a conventional rigid pin joint. Craft also uses a crossbelt mechanism, so the dip and pip joint both bend equally and simultaneously. So in the simplified diagram, if the left side moves down, it causes the right side to move as well, and that is due to the fixed length of the orange and the blue line. And that's the less simplified model.
Okay. Our design allows the hand to absorb impacts without complex back driving control. And we use Frank mocap to extract body pose in order to teleoperate the robot end effector. And we use hammer to extract finger joint angles to teleoperate the hand. So next we highlight a teleoperation experiment where we pick up a delicate raspberry. Rigid hands struggle with this task. However, the craft hand only took half the amount of time to align and also did not crush any of the raspberries during the experiment. Here we have the hand grasping rigid objects like medicine pills, tennis balls, toy broccoli, as well as insertion tasks like plugs, USBs, and the key, as previously mentioned. We can also do soft objects like picking up the toast, wiping the whiteboards, picking up paper cups, plush toys, fruits, as well as finally picking up a glass. So we also have popular grasps that we can execute, all 33 of them. And yeah, for more details, refer to our paper. Thanks.
Great, thank you. Next, we will have is towards human level dexterous teleoperation here. Okay.
Video for this.
They have a video? Okay.
I have, okay, great.
We introduce teledexter.
Oh, let me turn it up. Can you,
Good
let's try.
We introduce teledexter, a method that pushes dexterous hands teleoperation towards human-level dexterity. Teledexter is a hand-object co-tracking controller for dexterous teleoperation. By tracking both the operator's hand motion and the object pose, it enables long-horizon manipulation with seamless contact transitions across translation, reorientation, and finger gating. In a series of tasks demonstrated, teledexter drives the dexterous hand to pick up different tools, reorient it in hand into a functional grasp, and execute its intended use, from tightening a bolt to driving a nail. Teledexter unlocks dexterous manipulation data previously beyond the reach of any teleoperation system. These demonstrations directly train autonomous policies for long-horizon dexterous tasks, establishing a scalable foundation towards human-level robotic dexterity. We also evaluate teledexter on primitive object reorientation. Cylinder, cuboid, and bunny test in-hand pose control over symmetric, edge and corner, and irregular geometries. The same framework generalizes across hand embodiments. Here, a four-fingered leap hand performs cylinder and cuboid reorientation using the same co-tracking learning and deployment pipeline. Different morphology, different actuation, same dexterous capability. We stress test teledexter with a continuous stream of randomly sampled target grasps. The controller must switch between arbitrary in-hand configurations on the fly, showcasing its versatile ability to handle diverse goal pose transitions in real time. Thanks for your attention.
Okay, great. We have two more, I think. So we have RealDex Umi next.
With those slides.
Yeah, the problem is I can't join Zoom. It's not working.
Yeah.
Wait,
Connecting directly. Do you have access to
wait, actually, never mind.
Oh, you got it?
I got it.
Okay.
The Zoom is Mishi's. All right, it's maybe we can just skip Zoom for these two. This one.
Yeah, so get the link. Maybe I can try downloading on here.
Yeah, but it's
Is it hard to download?
sure. Let's just try it. Click on Dropbox. It's just not working that well.
I see.
Sure why. Okay, I sent it to you on Drop. Are you on WhatsApp? Oh shit. Okay.
I got it on
Oh wait, never mind. I'm good. I'm good.
You're good. Okay.
Just super slow. Or just turn your.
Yeah.
All right, go for it.
Hi, my name is Zhuzhe. Sorry, the authors cannot attend in person, so I'll present this work on their behalf. The paper is called RealDex Umi, a wearable universal manipulation interface for dexterous robot learning. The Umi has enabled robot data collection to be more portable and efficient, but this is only for parallel grippers. To extend it to dexterous hands, there are many works that extended Umi for dexterous as a dexterous interface, such as the motion capture gloves on attached systems or Dex Umi. However, these devices either contains the retargeting challenges, has restricted workspace and wrist motions, or contain large visual differences and lack deployed hand commands. To address these limitations, we propose the RealDex Umi. The key idea is to use the same dexterous end effector during both data collection and robot deployment. So the device has two key advantages. The first is to be more deployable dexterity during the data collection, and second, it has less deployment gap during the execution. So then I'll describe the Dex Umi hardware design in detail. It contains several components. The first is dexterous hands with tactile sensors. It also has a camera and a tracker. And then the key innovation is the palm-side teleoperation glove. In this glove, it is very easy to wear, and it has the finger control with the springs, which makes the hand easy to open. And it also contains the magnetic encoder that can directly transfer to the fine-grained 6-degree of freedom robot actions. And during the data collection, the teleoperator can directly wear the arm and use it to collect data. And during the deployment, it uses the same vision, same touch, contact, and commands to be applied on the robot arms. So our RealDex Umi can support various dexterous tasks like twisting, precise tools or using, multi-object grasping, and long horizon articulated object interactions. There are many more tasks we can use this device to collect data. Using this collected data, we can deploy it and train policies and achieve high success rates with the ACT policy.
Zero gap data.
Yeah. And this model can be also deployed across different robot arms. So to summarize, we propose the real Dex-UMI, a compact wearable Dexterous interface with zero-gap teleoperation data collection. And in the next step, we plan to further extend it with global visual observations. Thank you.
Okay, cool. Thank you. Okay, so we got one more. I'll be presenting factor 2 on behalf of Stephen, Jason, and Tony, who cannot be here. Okay, force sensing is important but expensive. Franca costs over $30,000, and many other robot arms are even more expensive. And force sensors are also expensive. While there's some low-cost arms out there, they often do not have force sensors. Our question was, can we provide commodity arms with external force sensing without force sensors? Factor 2 allows for low-cost arms to leverage force information. First, we train next a neural external torque estimator, which estimates torque. Second, we use this for force-informed resampling and training in behavior cloning. Let's see how next works. First, we move the robot arms around in free space. This free space allows us to collect the data, and it collects 10 minutes of joint position, joint velocity, and motor current information. We do not need dedicated force torque sensors for this. Next, we train an LSTM on this data to predict a free space torque. This LSTM takes in joint states and predicts the joint torque in free space. And then in deployment, we can use that prediction and subtract it from the measured joint current times a constant value to get us the external joint torque estimate. Next produces high-quality torque estimates on low-cost robot arms for a variety of different tasks. And we find that it's relatively easy to use for a variety of different operators. Next, how can we leverage to learn external torque to improve BC policies? First, what we do, we segment the trajectories into contact phases based on the external torque into free motion, pre-contact, and contact areas of the trajectory. Next, we upsample the pre-contact and contact data during BC training. We can see that in a base policy that the validation loss is higher. However, in first, we're able to train on pre-contact and free motion data and make sure that that validation loss is lower. This allows our policy to focus more on the contact time and post-contact part of the trajectory. We can see on a variety of different tasks, and we're able to complete on our robot arm and hand system. We can see compared to a baseline without first, that it's difficult for this robot arm system to put this belt onto the, but with first, it is easier to put this belt on and it's able to recover better. This is because the policy is focusing more on the contact and post-contact phases. Cool. And you can see more on our website. Thank you. All right, hopefully you guys had a great break and people are filtering back in. I'm happy to introduce Oliver. Oliver Brock is the Alexander Professor of Robotics at TU Berlin, where he leads the Robotics and Biology Laboratory. In Dexterous Manipulation, his laboratory is particularly known for its work on intrinsically compliant robot hands, including pneumatically actuated ones, and for exploring how morphology and control can work together to enable robust grasping, in-hand manipulation, etc. His contributions have been recognized with lots of honors, so I won't list all of them, but including the RSS 2016 Outstanding System Paper Award. Thank you, Oliver, for being here. Go for it.
Yeah, thank you very much for the nice introduction and for having me. Yeah, I think I'm going to do a little bit something different to the previous talks. I actually want to talk together with you about the problem that we're trying to solve. And to get a starting point, I'm going to go back to the text that was written on the homepage of this workshop. And it reads that Dexterous manipulation is entering a pivotal transformation in this year, and that the bottleneck of this grand challenge is shifting. the statement is that we're moving from a scarcity of hardware to an era of accessible and robust hands, and that rather than asking ourselves, how do we control these hands, we ask ourselves how to scale dexterity by leveraging massive video datasets, hardware, and so on. And I think that pretty much describes what we've seen so far, right? Even in all the spotlights, people do have dexterous hands now, and people are using massive video datasets and so on in order to achieve manipulation, dexterity. Still, I think that I'm a little bit skeptical, and I want to share this skepticism with you and see if you agree or not, and maybe we can continue then having a discussion about this during the panel session. I think this hand, the sharper wave, kind of had an impact on our field. People think it is kind of the path to dexterity, and if you see what it can do, you see often this particular configuration where all the hands, all the fingers are set up in a symmetric tunnel, if you want, around the object and are spinning things. The question is that really all there is? Or is that something that gives us the illusion that we're really tackling dexterity when we're tackling one particular aspect of dexterity that is particularly simple, right? Could be. And then another selling point of these hands is that they have very high density tactile sensing in the fingertips. And I wonder, is it enough to have tactile sensing with high density in the fingertips? Or do we, rather than having high density, need sensing all over the hand? Right? And so if these things are true, then maybe the sharper is not the final answer that we need in order to break through this barrier of dexterity. And just, I was reminded as I was preparing this talk of this hand that was introduced, I don't know, 20 years ago. There's a video, if you can actually hear the sound, probably not. But basically no, you can.
Switch allows the hand to drive 8 axes.
At least in the room you can, maybe.
Which automatically redirects torques to the joints requiring active power. Within milliseconds of a finger's inner link making firm contact with an object, the torque switch locks that link against the object and redirects that finger's motor torque to the outer joint. The outer link then continues to secure the target object.
So there is a short segment from, advertisement video from Barrett Technology, but it shows that already 15 years ago, we were thinking about having hands with joints that are compliant and building that compliance into the mechanism and doing so successfully. So I don't know. I'm a little bit skeptical that we really have cracked this nut. And in order to kind of have a debate with you about this, we first need to define kind of what is this nut? What is really dexterity? What is manipulation? What's the challenge? And I think, we keep doing this. I'm going to keep doing this also. Jeannette showed a video of human dexterity to motivate why we needed fingered hands. I'm going to go back to a really old video. The video is actually from the 60s. The first time I've shown it is probably 13 years ago. And it's from a cooking show. From 1963. It's a 5-second video, right? And during those 5 seconds, so many things are happening. So we had the discussion earlier, or the question was asked, can we do everything with 2-fingered grippers? I don't think anything that we saw here can be done with 2-fingered grippers. By the way, nothing we consider a grasp in the sense of force closure happened here, except for holding the knife. Everything else is something else, but it's somehow dexterity. And I would like to suggest that what's really going on here is something that is called the exploitation of environmental constraints. Environmental constraints are interactions between the robot, the agent, the hand, and the environment that leverage feedback from the environment in order to simplify a planning, control, or perception task. And to illustrate how many environmental constraints were being exploited in this video, we've annotated these different exploitations in this video. The details do not matter. In this 5-second video, we caught over 30 exploitations of environmental constraints. And all of them are based on contact, right? You can have environmental constraints based on vision, but these are based on contact. Now, the question is, if environmental constraints are something that is so fundamental to manipulation, why don't we actually think about it from this perspective? In order to do that, we first need to kind of validate that it's indeed the core of manipulation. And we did this also. This is also very old work from over 10 years ago, where we designed such a setup to test human manipulation. There's on the left here, you see kind of a usage box where people needed to pick up credit cards to use them or keys to insert them. And we had thousands of experiments conducted with many different human subjects under a number of conditions. Two of them I'm going to talk about briefly here. One is where people were put on goggles that had frosted glass in them to impair the vision, right? So, and the other one is when there was a hot charcoal displayed on the table surface, illustrating that people were not allowed to use the table as an environmental constraint. And obviously the idea was that when you view the world through frosted glasses, you have much more uncertainty about where the object is, what the object is, and in order to compensate from that, you're going to increase your use of environmental constraints. And if the table surface is glowing charcoal, basically you're prevented from using this thing that you need fundamentally to be robust, and your robustness is going to go down. And that's exactly what we observed. 3,400 grasping trials. There's 25 different objects that you see here. A subset is here. This is the regular vision. This is the goggles, and this is how you see it. And you see here single experiments of these 3,400 person picking up with the normal vision on the left and with impaired vision on the right. And when you trace the contact patches that the hue had with the table surface, you can see that on the left, when the vision was good, there's very little contact and there's short contact. On the right, when the vision was impaired, the human, as we predicted, uses much more of these environmental constraints. This was just a short glimpse, right? We have 3,400 experiments. All of this is published. These are the 4 people that did this: Marianne Mertens, Steffen Puhlmann, José Antonio Alvarez Ruiz, and Fabian Heinemann. But we took this as very solid confirmation that human dexterity is intrinsically linked to the exploitation of environmental constraints. Jeannette earlier mentioned these force-guided actions or force-informed actions. The forces that are informing the actions are exactly those forces that are derived from environmental constraints, right? Because forces by themselves could be bad or good, but it's if they are derived from environmental constraints that are useful for the task, that's when they help. And so we build a hand. This is actually the 3rd version of this hand that maximizes compliance so that we can engage in contact. We can exploit these environmental constraints, assuming that that is the key to dexterity. And then using this thing, we can actually use the environment in very simple ways to pick up objects like this one, like this ticket, in a way that looks very human. You can also do manipulation. This was work from 2021, maybe, where basically based on these environmental constraints, we can program these hands to do this work. And then people said, oh, but you're using the palm up configuration. And we said to them, we don't care. To them, somehow that was really important, whether the palm was facing up or down. So here we start off with the palm facing up, and we do some in-hand cube rotation. And we've done this for all kinds of different objects, different shapes, different weights, different sizes. And then when you start moving, so you change the orientation of the palm, that doesn't change, right? So it's robust to these variations in gravity, or where the palm faces. Basically, this generalizes very, very strongly across object sizes, weights, shapes, across execution speed, can be performed hundreds of times in a row, is really, really robust as a consequence of these environmental constraints. And we've gotten this to the point where we can actually have a planner, right? So here you see up, unfortunately, my video seems to be freezing. I hope it recovers. But on the right, you see a sequence of goals. We want to spell RBO with the name of our lab, TU Berlin, the name of our university. And this is a plan that was generated by a planner based on planning sequences of environmental constraints. And sorry about the video. And the way this works is we use environmental constraints to characterize the capabilities of the hand. This leads to a huge graph, in this case, 93,000 nodes. And all the edges in this nodes correspond transitions between environmental constraints. If we're right in saying that environmental constraints are the key to robustness and versatility in dexterity, then any path through this graph should be feasible and robust, right? So that's what we've tried. We started a random node, and that's why this manipulation that you see here will not look meaningful, because it's a random walk in the space of capabilities that this hand has. But, you know, we can, and you hear the valves go on in the background. We take these random walks through the graph, and they work. Sometimes they don't really work, but you know, so here again it works. But if we wait long enough, there will be a path, this one, where basically it's stable and it does something, but it doesn't do exactly what we want it to do. So here's space for improvement, right? For doing something that involves learning. But overall, this works pretty well. And so this graph really represents the capabilities of this hand. Here is a subgraph that we just saw being executed. So what I've shown you is, number one, in humans, environmental constraints are really the key to achieving the dexterity that we see. What I've also shown you is that we take that and we turn the space of all actions of a robot hand into the space of all environmental constraint exploitations. We do that the right way. Then we get a graph that captures the capabilities of the hand, and we can execute anything we want. So that seems interesting, right? And there's no VLA, there's no data, there's no teleoperation here. What started was an insight about how humans are doing it. And maybe robots should do it in a different way, right? That's always possible. But we were kind of happy with the humanoid form factor. So why, if we take a human hand and we accept the fact that we want to copy the human, at least when it comes to morphology, it probably also makes sense to take a look at how humans are doing the control. Because control and morphology, by the way, should go hand in hand, no pun intended. So what's actually going on here? Why is it that we built this highly compliant hand? Why is compliance exactly the right approach to making dexterous manipulation? So very, very quickly, running through this, you see we basically, because we have these compliant fingers, right? They're made out of silicon, they're inflated by air, the whole thing is completely bendable, stretchable, and flexible. They act like springs. And when springs get deflected, they exert forces. Grasp of multiple of these springs apply a disturbance to a particular grasp, right? So here the original grasp object is shown in green, and then in light green is the deflection as a response to the disturbance. If you remove the disturbance, there's passive restoration as a result of these flexible, soft, compliant fingers having stored energy from the disturbance and giving it back to reattain the original state. So this is self-stabilization. This is what's in action, right? So you have here, Alexander is the PhD student who's doing this. He's pulling on this force torque sensor and is pulling this object inside the finger, and you see how it gets deformed, but when he lets go, it kind of reassumes the original position. By the way, I think this is the test you should apply to a hand before you buy it. Can it do this? Because if it can do this, you can leverage the capabilities of compliance to your advantage. If it can't do that, then you've bought something that's very expensive but doesn't really help you. All right, so that's the first level. Now we can basically try to take this self-stabilizing configuration and move it through the workspace. That is indicated here. We're actually actuating the hand to move the set points of the springs. These are the blue dots, to move them from one place to another, as indicated here, and that means we can move the object inside the hand. Oops. Yeah, this is an example of this happening. You see here an actuation for 0.5 seconds, and the rest of it is played out by the hand. So 0.5 seconds, you see the actuation starting, and now what you see, and notice that both fingers are moving, even though only the thumb was actuated. I'm going to play this one more time. Can I? So the hand itself, the compliance in the hand is executing a controlled motion that coordinates the index finger and the thumb as a result of being compliant. Here's an example of this happening in a more complicated situation. You see in the middle, you see the hand performing this set point change, right? And you don't really see anything. The middle finger is stationary because the set point doesn't change, and it's just these other two fingers that are changing. And around it, you see the video of the same actuation command that you see in the center being executed, but with many, many different objects inside the hand. And watch the middle finger, how it actually adjusts to really compensate, to remain opposing, to add robustness to this skill in spite of larger variations of the object. So you see here how compliance kind of really, really takes over an important part of control. Okay, so we put all of these things together. We basically have the spring on the left. The spring in a grasp configuration leads to this passive restoration. We then have actuation of the set points of the springs, which allows us to move the object. And we have the actuation of moving one contact point to another. We should call that gating. And that leads to this very discrete abstract graph that I've shown you earlier. And, basically we're going from the physics of the system on the left all the way to a discrete, good old-fashioned AI representation in which we can do planning. And to execute it, we simply, turn this arrow around and we get to something that looks like this. I hope maybe the second time the video plays, now it also gets stuck. Sorry about that. It's on our YouTube channel. You can watch it in all its glory. It's actually a very smooth and nice video. I don't know why it does that. Okay, so what is really the fundamental question here? Implicit in the announcement of this workshop was this idea that we have shifted the bottleneck and that we should now just do machine learning, right? Just use lots of data. That's my picture for lots of data. We should use lots of data on top of, by the way, on the bottom, it's a Lorentz attractor, right? It's a system that is not chaotic. It's actually deterministic, but if you change the initial conditions slightly, it diverges into something different, right? So this is exactly what characterizes manipulation. Small changes in the initial conditions lead to drastically different outcomes, and this is what we're trying to tame. We can either try to tame that with data, that's what's on the right, or I'm suggesting that we can use this layer on top of that, of environmental constraints, of compliance in the hand, and that takes care of us. It takes care for us of all of these challenges that this chaotic behavior of contact dynamics produce, and allows us to have a very simple graph-based representation of the actions. And we can easily combine that with large data in order to make that even better. But my point is, why would we throw away the insight that environmental constraints are the underlying structure of our problem? Yeah, why should we do that, right? Why should we throw that away? I think it's what we should use, and I think hands should be designed to allow us to use it. Thank you.
Great. Thank you for the talk. Are there any questions? Okay, over there.
Thanks for the talk. So you've produced a set of constraints with this hand. Are these the right constraints? Are these the same constraints as my hand have? Should I buy a new hand? Did you try to test it with your own hand, like the one you showed?
So the hand that I'm sorry, I'm speaking into the microphone, not trying to be impolite. So of course the hand that we have, the RBO hand 3, is not like the human hand. So it has different environmental constraints than the human hand. And by the way, human hands are not all the same either. People have quite different hand morphologies, and as a result, also have quite different strategies of how to manipulate. So I would say that the constraints that we extracted are for this particular hand, but we can extract this for any hand as long as you have a rough characterization of the kinematics and the material. So you give us that description, we build that graph for you, and off you go.
One more question, maybe?
First of all, thanks for the talk. When you mention like exploitation of environmental constraints, one of the things that comes up to my mind is support surfaces, where as humans we rest our elbows or forearms on surfaces that we know are not going to move, so that we can be more dexterous and precise with our motions on the finger side. Can you just sort of clarify, how does this sort of framework fit in with that sort of less prehensile type of exploitation?
Yeah, I mean, this is the obvious kind of way, right? The table surfaces. But if you look at in-hand manipulation, in in-hand manipulation, it's actually the hand that provides both the environmental constraints and the actuation. So the framework that we have is completely transparent to this, right? It doesn't matter whether an environmental constraint is provided by the wall, by a table, by the floor, or by a finger that is currently not, touching the object. All of these are completely compatible and should be used. I mean, and I think humans do this all the time, that you use various body parts as a recruited environmental constraint that is not in the environment, but you're creating it to facilitate a particular manipulation task. So yes, all of these things should be transparent and should be usable within your framework.
Awesome, thank you.
Great. Let's thank the speaker again.
Thank you. You kicked me out.
There we go. All right, so just a quick logistical thing. Apparently the PDFs for the spotlight papers were not working on the website. They are now. So if there's a particular paper you were looking for, there's a PDF button on the right of the title of the paper, and it should come up. Okay. Then the other thing is, so our next speaker is Hao-Shu. Hao-Shu could not be here in person, but he will be presenting on Zoom. Hao-Shu Fang is a postdoctoral researcher at MIT, will soon join the University of Maryland as an assistant professor. His research focuses on dexterous robotic manipulation, spanning tactile sensing.
Oh, hello, hello.
I'm muted as well. Okay. Hao-Shu, can you hear us?
Yeah, I can hear you.
Okay, great. Can you screen share and start presenting your slides?
Okay. Okay. Can you see my slides?
Yes, looks good.
Okay, thank you. Yeah, hello everyone. I'm Hao-Shu, and I'm happy to present today. So today I'll talk about perioperation, like a way to sensorize human for scalable dexterous manipulation data. And basically, I think today I will introduce like how we can solve like dexterous manipulation from a data perspective. And I hope that through my talk, well, you can basically understand what's happening here, which is I built a exoskeleton to sensorize and capture my manipulation and transfer my skills to the robot. So the background is nowadays there are many humanoids and they're equipped with dexterous hands. But one interesting thing is if we look at this manipulation, we will realize that actually in most of these demos, the robots are using their hand like a gripper. So if you look at like each sub-videos carefully, we will soon notice that fact. And I call it dexterous dilemma because I think the reason we build a very expensive dexterous hand is not to just use it in a way that you open your hand, you reach an object, and then you close your hand and move the object to another place. But we build a hand because we really want to achieve some truly dexterous tasks. For example, using articulated tools, reorienting objects in our hand. And most importantly is to manipulate small objects, such as screwing small nuts and bolts. And these kind of tasks are pretty hard to achieve nowadays. And one important problem is because we rely a lot on machine learning technique nowadays. But this kind of data is almost impossible to collect via teleoperation. So how could we solve this kind of a data problem? Well, if we look at our human, we are doing this kind of manipulation every day. So people are proposing different kind of approach to collect human data. For example, from ego video or like using UMI gripper. But for me, I think basically they denote the same thing, which is to build some device that can capture human daily manipulation and also, human daily observation and our action pairs and store this kind of data for robot transfer. So I would like to call this kind of approach perioperation because I think sensorizing humans with some actual devices and also maximizing the transferability is really a good approach. And also the name peri comes from teleoperation because peri is contrasted with tele in Greek. So I also believe this kind of approach is very suitable for humanoid dexterous manipulation because it directly sensorizes humans. And one of the reasons we built humanoid is because we want to maximize the data transferability from human to robots. So I would like to present one of our recent work, Dexo, which is a data device that can capture human dexterous manipulation, especially like human hand movement as well as tactile data. So I'll introduce this work from three perspectives. First is what is needed to achieve a dexterous manipulation with this kind of device. And second is how we can build this kind of device. And third, like why is this a better approach compared to teleoperation? So first of all, like what is needed in terms of data when we try to build this kind of device, like what kind of data we need to capture. So first, in terms of observation, of course, like vision is very important. But besides that, tactile is another important modality. I believe some of you have seen this video, which is like if you like a scientist, like they inject some drugs to a human subject's hand, which numb their sense of touch. However, the human can still move their hand freely. And in this video, we can see that without the sense of touch, it becomes dramatically difficult even for human to accomplish a very simple task, which is striking a match. So it means that tactile is very important if we want to manipulate small objects. And the second thing is, in terms of action, what do we want to record? So of course, like finger pose is very important, but besides that, we also want to capture the torque information. So for example, if you didn't capture the torque, then when you are like trying to duplicate the skill of holding a bottle, you won't be able to apply the correct amount of force. So the bottle might just slip from your hand. And eventually we really need this kind of device to capture the data and then transfer the data onto the robots. So we hope that our device can also mitigate the embodiment gap of human and robots. And in terms of the form factor of this kind of device, some people might say, can we build a data glove and capture manipulation data out of this glove? So there are several things that I think nowadays data glove is not good enough yet. The first thing is, for most of human dexterous hand nowadays, they still have some kind of mismatch with human's hand in terms of kinematics. And also different humans who have different kinematics. So this kind of mismatch of human and robot hand could make learning more difficult. The second thing is, nowadays tactile glove, the tactile resolution is usually not high enough. And it's still an open question that whether this kind of low resolution tactile sensing is enough to enable general dexterous manipulation. And third, there are some high resolution tactile sensors, but they're usually bulky to directly incorporate it into a tactile glove. So that's why we are not using a data glove for this purpose. And in order to achieve building such a data device, now we have two constraints. So one constraint comes from the human hand, which is we want to make the device that's easy for humans to wear. And the second constraint comes from the robot hand, because we really want the data to have as small embodiment gap as the robot hand as possible. So it's a very difficult problem. And our solution is we want to co-design the hand and this kind of Perioperation device so that you can maximize the data transferability. And that means you really need to start from building a dexterous hand that's close to a human's hand so that it decreases the difficulty or lower the bar to build such kind of a Perioperation device. So in 2024, we start building the dexterous hand, and Brendan is the main author in building this kind of hardware. So we try to focus on three aspects of a dexterous hand to make it closer to that of humans. The first part is we try to make a hand that has pretty good tactile sensing. And in eyesight hand, we incorporate a whole hand tactile sensing system using a high resolution gel side-like tactile sensor so that you can actually feel the very fine details, like geometry details of the object that you are manipulating. And the second part is to make the hand as compliant as human hand, because robot hand, they will have very rich contact when they are trying to manipulate object. So we believe that the compliance is a very important form factor. And the third part is we try to make the form factor very, like, especially the kinematics of the robot hand as close as possible to human's hand. So in the eyesight hand, it's a 7 degrees of freedom hand, but we try to arrange those like in a similar pattern to a human's hand. Then after we have this kind of robot hand, we can build a data device that try to bridge the human hand and the robot hand. And the way we make it is also simple. So first we take out the CAD model of the actual robot hand, and then we remove all the actuators enclosed by the orange circles. And then we get a passive hand. And on this passive hand, we put position encoders at each joint to record the joint angles. And then at this passive hand, with this passive hand, we then build a wearable exoskeleton where humans can put our hand into. And eventually we build some standoffs and linkage systems to connect the wearable exoskeleton with the passive hand. And in this way, the linkage system could transmit force between the passive robot hand and the actual human hand. And it also helps reduce the degrees of freedom from human hand to that of the robot hand. And in this way, like, the data you collected with this kind of exo literally have the same kinematics as the actual robot hand. And this video demonstrates the data format captured by our data device. So you could see that it captured whole hand tactile sensing signal, and also the kinematics or the hand pose of the passive robot hand. So with this device, you can achieve many different kinds of dexterous manipulation. For example, you could pick up a very tiny M2 bolt and try to screw it onto a M2 pin. This kind of manipulation is pretty difficult because you really need to feel the small vibration and tiny force when you try to grasp the M2 bolt. You can also try to do some in-hand reorientation in a very efficient manner. So nowadays, there are some algorithms that allows humans to do teleoperation to collect in-hand reorientation data, but usually they're still not very efficient. But with EXO and with direct force feedback, you can do in-hand reorientation in a very efficient manner. You can also try to operate a syringe. So in this case, you also need to reorient the syringe and then like try to do a functional pushing. So besides fingertip manipulation, there are also many tasks that involve whole hand manipulation, which need the support from the palm. And with this kind of device, you can also collect this kind of full hand manipulation data easily. For example, you can flip open a seasoning bottle. Or you can try to use a paper cutter. So in this demo, you need to squeeze the handle to pop out the knife of the paper cutter to really cut or use it to cut the paper. So we try to have a comparison with kind of this approach with teleoperation. And here the teleoperation, it's completely based on visual feedback. So it means that there was no force feedback in the teleoperation system. And we tried to collect demos for a simple task, which is to package a small box. And with Dexterous, it takes us around 10 seconds to accomplish the task. But with teleoperation, it took us around 70 seconds. So this demo just demonstrates like how efficient you can collect data with our device compared to teleoperation. And we conduct this kind of comparison across 6 different tasks, including bottle opening, bulb installation, like box packaging, drilling, hard disk assembly, and cardboard folding. So on the first 3 tasks, with our data device, you can achieve 2 to 7 times higher efficiency than teleoperation. And in the latter 3 tasks, you cannot even accomplish the task with teleoperation. So with this kind of a device, and also in our previous work, we tried to build an ARM-based exoskeleton called AirExo. And by combining AirExo and Dexterous, we can use this kind of upper body data capture device to like record my daily manipulation, for example, bulb installation, and then transfer the skills onto the robot. And this video demonstrates like all the data you can collect out of our upper body ecosystem. You could collect the wrist image from the left and wrist camera. You can collect the fingertip tactile sensing system. And you can also record the whole body joint states. And then by using this kind of data, you can train a policy and then try to transfer the policy onto the robots. So in this demo, we combine part of teleoperation data to try to mitigate the embodiment gap of robot and humans. But in other work, we also try to directly learn policies from the perioperation data. So one gap we need to solve here is the visual gap. Well, and the problem is that if you try to just use a in-hand camera, there might be a very small visual gap between this kind of human data and the robot data, because the camera is mounted at the wrist, and what you see is basically the end effector. And in that, from that perspective, the embodiment gap of human and robots could be small. But we actually found that if you just use in-hand cameras, the performance of the policy would degrade. So we tried to make or conduct an ablation study. And for this kind of pick and place task, it's very simple. And we tried that with one global camera, you can achieve like around 45 success rates. But given the same amount of demonstrations, if you use 2 in-hand cameras, the success rate could improve to around 60%. And eventually, we tried to combine global and in-hand data. And we found that the performance goes to like 72%. So it means that given the same amount of demonstrations, adding one global camera could increase the success rate by a large margin. So there's no reason that we don't want to use the global camera if it's available. And in some other scenarios, like we want to have or train a 3D policy because there are some papers demonstrating that if you combine point cloud, you can further increase the generalization capability or robustness of the policy. But one problem of in-hand camera is that there will be some dead zone issue. It means that if the in-hand camera is too close to the object, then the point cloud is out of the depth camera could be completely missed. So that's another reason that why you want the global camera. And the problem, yeah.
Can we give you like a 2 or 3 minute warning? How many more slides do you have?
I think 2 or 3 slides.
Okay, perfect. Keep going. Sorry.
Yeah, thanks. So one problem with global camera is that you have this kind of visual mismatch from the actual data, human data versus the robot data. But thanks to the nowadays visual foundation model, you can really do a visual adaptation. So you can basically like paint human and robot, exoskeletons, and then do an image in painting. And also, since you recorded the robot actions, you can render a robot image and then try to generate a vivid robot image by ControlNet. And eventually you can transpose this kind of robot image onto the background. So here I would like to show 3 videos that demonstrate like what kind of data you can get out of the exo data. So you could see that you can actually generate pretty vivid robot videos. And that's also how we solve the visual gap between this kind of exo data and the robot data. Yep. So I think that's all of my talk today. And one last thing is you can also try to generate point cloud data from this kind of approach. Yep. And that's all of my talk today. Thanks. And I'm happy to take any questions.
All right. Thank you, Hao-Shu. We'll cut the questions really short. Maybe if there's one quick question, go for it. I can repeat it if you can't hear it. Or you can come up here, yeah.
This microphone or?
It's laptop, yeah.
Hey, just a quick question. So, I mean, ultimately, the goal is to kind of recreate, depending on what sensing modalities the human takes in, how he reacts and how he acts. And in teleoperation, the human often just gets the visual, and what's super cool in Dexo, the human also gets the force feedback in some ways. But however, what's missing in the device is the transmission of the tactile information, but yet you're collecting it. So how do you, if you could just comment on this gap.
Yeah, that's a very good point, because something we also realize that is in terms of small object of manipulation without tactile feedback, although you can do it with pretty good force feedback, but it's still very inefficient. So I think one way of future Dexo or this kind of Perioperation device in future is to really revisit the piezoresistive based tactile sensor and make them very thin so that you could just wear this kind of thin tactile sensors and also allow humans to feel through it to have very good tactile display.
Great, thank you.
Thank you.
Okay, now we will switch over to our panel. So the room's kind of awkward, so maybe we'll have the panelists sit up here roughly. Don't really have any other choice. So we'll have panel questions for about 30 minutes. So if you have questions, you can sort of raise your hand and we'll try to call on people. I'll also moderate the panel and throw some questions in as we're going. We'll have panels. I think this will work. I don't know if there's like a camera we can. This actually.
I put in person.
Oh,
I don't know if that helps.
That's actually not the worst. Yeah.
Okay.
Okay, so I guess we'll have there's one more chair there, and then we'll have
Hao-Shu, you'll be on Zoom. Hopefully you can hear them okay. I guess we'll just have to see how
Yeah.
not much we can do about it. Do we have microphones? Yeah. So these ones will work?
Yeah.
Both of these will work?
Yep.
Okay, then that'll help.
It works.
Okay, and then maybe as
Maybe you can scoot
Maybe you
in
can
a
use
little.
one, say, for the audience and one.
yeah,
Thanks.
Yeah.
probably for the best.
Okay.
Okay. Great. So I guess if you are in the audience, you want to ask a question, you can raise your hand, or I can throw a question in as well. Let me throw one in. Or okay, go for it.
So many of the talks we saw, you discussed in some way the morphology of the hand to some extent. So how many fingers do we actually need in a hand? So, I mean, like, I think we started in Jeannette's talk from 2, and maybe 2 is not enough. And then I think, Oliver, your question more, or you said, if we assume the morphology, then so what should be assumed? Like do we need to go beyond 5, or is 6 fingers enough, or 7, or
I'll head at 6.
Yeah, sorry, I can maybe start give an answer. I think the cop-out answer is it depends on the task, right? But okay, if you can do a lot with a gripper or with 2 grippers, right? Like as we all observe. But I think what additional fingers can give you is again higher throughput, more controllability, or the higher throughput comes from the additional controllability. So again, and also, do we need anthropomorphic hands? I don't know. I think there are really cool designs out there that are not anthropomorphic at all. Yeah, so I think it's very task dependent and also dependent on the requirements you actually have for the thing that you want to solve. If you're, let's say, a small business or a large business that had particular tasks that you would like to automate, then maybe these tasks come with specific throughput requirements actually, or other requirements, and that might dictate what the design should look like. So I don't think there's like one general design. So yeah, I don't have like a definite answer, but maybe others have other thoughts on this.
Thanks for the question. I think I completely agree that it is very task dependent, and in fact, parallel dual grip is what it can do, a ton of tasks already, and so but there are arguments to be made that in the future, if we want to kind of learn large scale from videos, then we want something that looks like, a pair of human hands. It's, nicer to do retargeting that way. And I suppose the upper bound of things that can be done is at least for researchers, it's something that would be kind of interesting. So it's also that humanoid argument, right? So if we want to make something very general purpose, then we want it to kind of mimic the human because the world is designed around us. So, but as a research problem, no, but but as a research problem, I think the fact that a lot of the hardware is kind of maturing around Dex hands, that's kind of a nice opportunity.
I'll just add something quickly there. Your question really is not finished with what you said, because you didn't specify what actually the task is, right? What your goal is. And in the end, I think my question will be, why do you care? If you define what your task is, and I give you a mechanism that does it with 12 fingers, or 12 fingers and 6 other appendages, whatever, right? You're going to be happy. So really, it's a question of co-design of control and morphology, given a particular set of capabilities that you want to achieve. So do you really care about the number of fingers?
Maybe I should have asked, with the barrett hand that you showed, that looked
it can do quite a lot. Have we tried hard enough? Absolutely, we have not tried hard enough. Right? As a matter of fact, I think we kind of stopped trying. Right? We stopped thinking about the problem and we're delegating it to some large neural network to figure it out. So yes, I think we've not tried hard enough.
Maybe people don't want to try hard. But also, I want to give a shout out to Matej, your colleague. Sorry, I'm probably not pronouncing his last name correctly, but he just developed a three-fingered hand and designed it in such a way that it actually gives more dexterity, as I called it, than, for example, the varied hand. Although I agree, the varied hand can do a lot of things, but I just want to point at this work as well.
Okay. Yeah, I think previously at MIT, so one of the reasons that we built the eyesight hand was Ted was trying to figure out what's the smallest number you can get to support good dexterity. And in that project, Brendan designed a three-finger hand. And what we observed was that three-finger hand is, I think, as Jeannette mentioned, it's about efficiency. And three-finger hand, you can use it to do some, most of the dexterous manipulation, small object assembly. But we also realized that the fourth finger is useful, when it comes to larger object manipulation, to provide additional support.
Yeah. I mean, my also question, I guess, following up on this is when you buy one of these robot hands, you can't pick what they look like a lot of times, but you can pick which hand you want to buy. And what is your wish list and what is missing? It seems people are gravitating towards so many right now versus even a few years ago.
Yeah, my wish list is it should be robust hardware. And so if that hand doesn't look anthropomorphic, but I can do a lot of things with it and it doesn't break all the time, or I have support by the company to actually give me maintenance. That's one really important thing. That's just a really practical thing that, by the way, anyone who uses a robot head will need at some point. The other thing is compliance for sure, and a high control bandwidth as well. Yeah. I don't know about tactile sensing. Again, I think it's very task dependent. But yeah, maybe in that order.
I think one of the experiences that I had was around some of the kind of newer hardware, the kind of 20 DOF hands out of China that it was so robustness is the kind of the factor there that it would that a lot of the stuff is still quite in its early days, so it was not robust, but the supplier was really nice in that they just sent me another one. And so so I feel like having at least for a lab having support to because Dex hands are fragile, so having that support is great. I think overheating is one thing that we've found kind of a lot of the commercial hands out there really suffer from, because as you're collecting data, you collect for a while and then you have to let it cool, and then it's just not ideal. So if that's something high on the wish list as well.
Yeah, the overheating is kind of crazy, right? Yeah. I mean, it's an indication, I think, that we're following the wrong paradigm to build hands. But I think I've spent the last 15 years building the hand that I want. So that's the one I would get. It's super easy to fix. It's super cheap. Everybody in my lab can build it. We have 50 of them laying around. So everybody can use it. If it breaks, we just, replace it with another one. And I think it's pretty capable.
Yeah, and I think your hand looks different than everyone else's, and it's a good thing. Yeah.
Well, of course it looks different, but in what sense do you think it's actually different?
I mean, I think a lot of these hands are much more rigid, right? And they're not thinking about compliance.
Absolutely. In that sense, it's very different, right? It's completely compliant. And actually, you know, the ArborHand 2 was built with the goal of maximizing its compliance. And in the ArborHand 3, we tried to keep as much while adding much more degrees of freedom so that we can reconfigure the compliance to get the compliance mode versus the stiffness mode that we need in different directions for a particular task.
Right. Yeah.
Yeah, and none of the hands that you can buy for, I just learned that the sharper hand is 80K.
Yeah.
I mean, yeah, none of these hands can do that.
Yeah.
And by the way, on our website, we have videos and shopping lists, and you know, all of you can build this hand.
Yeah, that's great. I also agree a lot in, compliant designs and, bringing hardware out there like that. Yeah, it's great work. Are there other questions maybe, or Hao-Shu, you have anything?
Oh, well, I think in terms of feature, so my personal choice is like very dense tactile sensing and compliance. But beyond that, I think one important thing, like when I try to buy things, is I really care about the batch consistency, because like in lab, when I did experiments, like for example, collect data on one hand or deploy a policy on one hand, and then if it breaks and I need to switch to another hand, so I just hope that my data or my policy could have the same performance on the new platform. And in that sense, I really hope the hand could have a very good batch consistency.
But isn't that rather an indication that that the policy is wrong? I mean, you know, when you wake up in the morning or when you go out in the cold, your hand is actually physically very different. But you don't really need to relearn anything, right? You have built that into your policy to compensate for that. You've learned feedback strategies to adjust. So shouldn't we, rather than overfit to one particular day, because you know, if it overheats, the mechanical properties change, right? If it's humid outside, shouldn't we come up with policies that are robust rather than demanding?
Yeah, that's really the goal. But it really depends on whether you can achieve that in lab. So the goal is like that's about generalization capability. But in many scenarios, if you are focusing on each paper, you might focus on dexterity or like other aspects of the problem you want to solve.
Sure. Should we go to the next question then?
Yeah. So I want to ask a question about the learning paradigm. So if we imagine the human babies when they were born, they're constantly interacting with the environment to play with the toys without any particular goals, and they learn this continuous stream of the interaction process that sometimes they fail, sometimes they succeed. And we see today we are now building a lot of devices to capture the data, such as the Dexop and many other Dexumi-like devices. So those are, I would say, kind of passive data acquisition system. It's not like when a human baby is playing with the toys that they gathering a bunch of failure and success trajectory all day long. So yeah, I want to gather some of your opinions about is that the route that we have to go in order to make the dexterous manipulation really capable of doing a lot of things, and what is the reasons behind that? Yeah.
Okay, I can get started. So there was lots of things in this could give the context that you gave. There were lots of different aspects. One was first of all, you started off with a baby. That baby is growing, so their body is changing. That's crazy if you think about it from a robotics point of view. Just talking about this batch consistency, for example. Then the other thing is, okay, you said something about this baby is collecting all this data, right? And you contrasted that with the passive data collection that we currently sort of do, I guess. You use that word. And then the other thing was and I think that was it. But you said like you were asking if we should follow that paradigm of like having a baby just play
It's basically contrasting the passive data collection versus the active paradigm. Yeah.
I see what you're saying. Yeah, it depends what your goals are. I mean, okay, maybe one thing is like if you look at how again we grow up and learn all these things, like people say like, oh, in the lifetime of a baby or of a person, you collect so much data and it's comparable to the amount of data that maybe we need to train these large models, and there's evolution and blah blah blah. But I think somehow, when I actually look at how well all these ELAs and whatever really work, I don't think it doesn't seem to me that we should follow this particular paradigm. I think there's like a bunch of more breakthroughs and research questions to be answered to actually enable that kind of adaptivity and continuous learning that we see, as well as this more deliberate learning about how the world actually works, and be more active about it, of what you select to learn and what you try to practice. I mean, I don't have the answer how, but I think that we are not at the end, right? Like we have not discovered the final answer. I don't think so. I think to get there, we still need a lot. I mean, just think about how much power this baby actually uses to act in the world. I mean, our brain needs like 200 watts. I don't know about babies, but ours right now uses 20. Okay. So, and that's really different to the nuclear power plant that is used to train these models. So I don't know. So I think there's lots to do and lots to discover still to make robots actually be that as capable as humans.
Yeah, really agree. And I think to add to that, this aspect of continual learning, something that has kind of arisen, at least from the BLA community and imitation learning community over the past year, is there's seemingly quite a focus on like RL post-training. So you would collect data somewhere, and generally that's kind of clean, and then hopefully during deployment, you have a human go and intervene, and then collect corrections and collect data, and kind of try to or attempt to build up a data flywheel and use that for online RL. And I think and I think this is quite a kind of emerging and hot direction, at least in the BLA community, and hopefully that links up to kind of the continual learning stuff.
I think we haven't figured out Dexterous manipulation yet. I think that's safe to say. And whenever that is the case, I think a multitude of approaches is the right way to go for scientific community. So we should try all kinds of things. And maybe even more importantly, we should try them together. We should not be methodological ideologues. We should take, ideas that work and use them. So talking about your baby, the baby is actually solving a more difficult problem than necessarily what we have to solve, because it has to learn the right representation for its whole sensory motor loop, and it has to learn the domain knowledge it needs to do manipulation. And maybe we can separate that in our robots. We have the luxury to do that, the baby doesn't. So we can have a simpler problem that we solve on the robot. And I think we can use human insight to really help us along, right? If we understand something about the representation, and you heard my talk probably. I think environmental constraints are kind of the language of dexterous manipulation. If we know that, then we should use that somehow, right? The kid doesn't know it; the kid has to figure it out. We're in a lucky kind of situation that we can actually inject that into whatever approach that we decide to pick.
Guess we'll go on to next question. Are there other questions?
Does the panel have a question?
Sure, panel can ask questions to the rest of the panel, I suppose.
Yeah, thanks for the great discussion. A lot of the discussion was around hardware today, right? As a computer scientist, I think sometimes we have this inclination to automate the hardware design and talk about the software hardware co-design loop. So my question concretely is, if we don't know what task we're solving and it's very task dependent, how do we think about this hardware software co-design loop? I know you, Oliver, you have done some work in this space. You have some streets of tasks, but like in general, how do we tackle this hard problem? And in future, can we automate this design and think of superhuman hand design?
I think you're asking a very difficult question. I feel like as a field, we're coming from a situation where we kind of defined a task that was, crisp. I don't know, peg into hole. You can see the peg is in, the peg is out. It's very clear what you need to do. Two, we would like our systems to generalize. That's a very different kind of task to generalize. It actually is exactly the next step beyond any of these specific task definitions. Because whatever you define, whatever set of tasks you define, that now is your task, and you want to generalize beyond that. Right? And then you have new tasks, you put that in your set. You want to generalize beyond that. So generalization is always the task you didn't think of yet. And honestly, I don't know how to articulate that. I don't know how to test for that. I don't know how to compare systems that exhibit this property. But I know that all of us talk about generalization all the time. And my feeling is that few of us really know what that means. So I think we should work on answering your question. Sorry, that's the only thing I have to say at this point, but you're already rubbing your hands.
Yeah. Okay. So yeah, I also worked a little bit of co-design, and this is exactly this problem that we saw, right? Like that if you do this, you kind of like design something that is very specific to this task, which is kind of unsatisfying. But one thing to think about is maybe that I mean, our hand again, like we all have the same sort of hand, most of us. So, but we're using tools. And so the way we deal with all of these different tasks is by developing all these different tools that are actually task specific, but our hand can use it, right? And so maybe that's a different way forward to, rather than thinking about co-design of the hand itself, what about co-design of the tools for a particular hand, right? Like, and so then you can make this hand more capable. It can use all these different tools that are useful for the different tasks. Maybe that's a different way to think about it, a more practical way. I agree with that comment as well. But to get around that question, think about the tools. I don't know.
The robot can make the next generation of its robot too, which is the tool.
Yeah.
Well, you pass the microphone, but I mean, the tools you just include them in the hand. That becomes your hand, right? Now your hand is that. Yeah. But you can have like your hand becomes the basis of a tool changer. So you have a hand that consists of multiple components. You can plug in and plug out. So somehow you cannot escape that kind of definition of the manipulandum and the manipulator, I think.
Hi. So one question I often asked by my other friends that's not working in the hand and robotics industry is that, okay, we're using hands and sometimes it's necessary to use tools, right? To, like, for example, when you're cooking stuff. Why not just have, as you just suggested, why not just have a simple tool changer, which is standardized, super cheap, and just develop tools for it? Like, why do we need a Dexterous hand but not develop a set of very cheap, simple, very targeted like tools that we can just swap onto the tool chain?
I think we've done that decades ago. Industry has lots of tool changing robots that have a whole bank, or sometimes it's a drum of tools that can rotate in place. And so people have done that. And I think it's not a different problem, right? It's still, you have a fixed set of tools for your application. If you now want to change what you build in your factory, you would require a new design of tools in that tool changer because they're so specific. And therefore, I think, we're still bouncing back to that question of how can we get something that is as versatile as the human hand, so we don't have to have specific tool changers for each task that we want to solve.
Okay, thanks.
Yeah, I think it's always about like why we wanna do research in this field. So I think it's like so for robots, people already start deploying it like decades ago. So the goal today is not to make robots deployable, but it's like how to reduce the engineering effort of deploying robots in the actual scenario. So I think as Oliver mentioned, like just studying dexterous manipulation provide a general way of enable robots to accomplish different tasks instead of switching between different tools.
And if we haven't figured out that problem, then we should have an automatic way of deciding for your particular application, a tool changer with these 12 tools is the right answer, right? That would be if we really understood what dexterous manipulation is.
Okay, one more question, and then I think we're running out of time.
Yeah, maybe you could say a human hand as a form of a tool changer. But my question is, so where's the first place you think that we'll see widespread use of dexterous hands in industry?
Nowhere. I don't know. Like when you say industry, what do you mean? It's like manufacturing? Do you mean like sorting trash? Do you mean commercial industry? So not home, not care. Okay. Could be. So everything. Okay. I don't know. I really don't think anyone's gonna use dexterous hands anytime soon. Because you know, grippers have just so much fewer parts and are so much more robust and actually quite versatile already that I'm not sure when people will, you know, it's a trade-off again, right? Like if you want to find the tasks that are really annoying and you want to automate, but that are also automatable, and you want to do it, you want to be able to do them really fast. And robustly without breaking things, and it's the cost trade-off and the robustness and time trade-off and all of this, right? So I don't know when people are ready to give a shot to dexterous hand that actually brings real value for this one particular task that they find so annoying, so that it needs to be automated and still is cheap enough. Right, so I'm not sure, but maybe other people have other thoughts. I just think it's really far out, and I don't know what would be the first one.
Thanks. I think because of the humanoid hype and kind of humanoid companies trying to like push humanoids into use cases, a lot of these humanoids have dex hands that kind of in a small scale, just as a kind of more of like a kind of low TRL prototyping type of thing. It might exist wherever the humanoids are placed. But it does seem like a lot of these companies, the main clientele is actually either education or occasionally entertainment. Yeah.
About 10 years ago, we deployed soft hands with an online supermarket to handle fruit and vegetables, because they are obviously in very different shapes and sizes, so you cannot easily standardize them. Sometimes they're nets, so it's difficult to do suction cups. And you need to be kind of gentle. If you have fruit, you can easily damage it. So I think if we had all of this packaged in such a way that it would be industrially reliable, right? So it works for 3 months in a row. I think then it would be easily deployable and it would be cost effective. I also think that in the large warehouse of online retailers, where they have these moving shelves and they stuff as many different products into each of these shelves as possible, getting stuff out is still being done by humans. And it turns out that the hand actually is pretty good at performing multiple actions at the same time, of pushing something to the side while moving towards the back, while grabbing that little thing and pulling it out, and at the same time preventing other things from falling out. So when it comes to these things, we don't know how to do it yet, but I think human hands or humanoid hands would be very good. So logistics is the short answer.
I disagree on the logistics, and the other because there's just so much money in doing it fast, and humans are really fast. I don't think I somehow doubt that it's the human hand. It's more about human decision making and versatility that they have personally. And so if you have a two-armed robot with a gripper, it would probably, if you figured out the decision making of it, it would probably be better and less expensive. But for the other part, the produce, the soft part of it, that makes sense to me. I don't think it has to be a dexterous hand, though. No.
Any last comments, Hao-Shu?
Yeah, so I actually asked some people from industry. Like it's very interesting because so previously I thought that if you are a big company and you are like manufacturing many products, you would try to automate your assembly line as much as possible. Like several weeks ago when I talked to a AC manufacturer, so I asked them like, you sell like, for example, thousands or like tens of thousands of ACs, like maybe every week. Why don't you automate your assembly line? And why are you still looking for solutions with, for example, embodied intelligence or like those fancy technique? And they told me that actually because they have too many SKUs, so they actually need to switch their assembly lines every day. So it means that each of their assembly lines, they are not like they might not like manufacture more than one product in a day. So, and in that case, it's very hard for you to design some automatable solutions to just for production or like improve your overall efficiency. But you really need to have a general solutions and also like the fancy dexterous manipulation in the assembly line to actually solve the problem. So that's just something I learned like recently when I talked to those manufacturers.
Interesting. All right, great. Let's thank the speakers for a great panel and all their talks. And I believe, so we're going to be switching venues after this, and I think we're kind of going to be walking, or at least there'll be a group of us who will walk together. I just have a couple announcements before we finish that. So one, I want to thank all the organizers, Hao-Shu's on Zoom, Jessica also for stepping in. It's been a great workshop. We also have a quick award for the spotlights. Maybe let's see if I can show this on Zoom, or I should have made a slide for this. But so all the organizers, even the ones on Zoom, looked at all the talks, the papers, as well as the posters. And we decided to award one Best Paper Award. And this is for the paper Craft, a tendon-driven hand with hybrid hard-soft compliance by Leo Lin, Shivansh Patel, Jay Moon, Svetlana Lezebnik, and Unat Jain. If one of the authors is here, great. Maybe we can get a quick photo we can put on Twitter or something. Wait, you should get in this photo too. I wanted them to.
There's two.
Yeah, there's two.
You guys-
Yeah. Great. Thank you, everyone. Hopefully we'll see you at another workshop sometime soon. Yeah. Oh, and also grab your posters, I think, or they will, I assume, get tossed since we're moving venues. Cool.